the staff coming at you. I have to remind them.
Karina still needs a SIM card, and Robertino has problems with his. So maybe sometime.
How
Sorry,
is that?
it's okay.
Can,
Yeah, maybe.
in the evening,
Yeah?
Westgate they close at 8, so we can go and check that.
Okay, sure. We can do it after class as well.
I just arrived.
The SIM card thing.
SIM
We
card
can do
issue.
it on the way back to the hotel.
Sure.
Yes.
Yes.
That's good. I'll tell Patrick to go to Westgate because they close at 8.
Okay.
That's it.
Thank you.
Okay.
Now we'll work with the cables.
Okay. Check.
Not yet. We.
Check.
Sure.
Good. Okay. $240? Okay. Okay, check. you. Okay, yeah, I know why. I picked the wrong resolution. It was 16 to 10 and not 16 to 9. Okay, seems to work.
If you want to, you can open and close the terminal of VS Code with Ctrl J.
I can't for some reason.
No?
I tried that.
Oh.
Maybe it clashes with my Vim or whatever, but I remapped it to control.
Okay.
For some reason, Control J didn't work. So my theory is that there's another thing that uses that, and somehow.
Maybe Shift.
I don't know. Didn't work. But I remapped it.
Perfect.
Oh, this is. Okay, should we start? Right, so today we are talking about polymorphism and type classes. So some of the things I'm saying today I already said briefly in one of the earlier lectures, but now we look at it in more detail. So first we talk about type inference. So as I already explained, the compiler will infer types for expressions and constants on functions and everything automatically. So you normally never need to manually supply a signature to anything. But you always can if you want. And as I already told you on the first day, for top level definitions, that's considered good style to always provide a signature. But normally the compiler can do everything automatically. So as long as you don't use any language extensions, then you never need a type signature. There are some language extensions that we'll see later that do require type signatures. But the standard Haskell 98, everything, it has perfect type inference, so you don't need any signatures. And as I also already showed you in GHCI, in the REPL, if you use :T and then some expression, then you're shown the type of that expression. So that's always helpful, but you should also over time learn to basically do the work of the type inference algorithm and like see the type of an expression itself, by yourself. Okay, so there's one thing maybe that's not on the slides, but I noticed that I was always tempted to use that yesterday, so maybe I want to start with that. So before we come back to that, and that's a very useful operator, $. And first of all, I also wanted to show you Hackage.
Can you zoom in a bit?
Yes, of course. Sorry. Sorry, that's different. So there's Haskell, there are many publicly available Haskell libraries, and they are all on the Haskell public package repository called Hackage. And that's at hackage.haskell.org. And I always, if I want to get information about something, I always but this is fine. For example, I always Google just the name of the library I'm interested in. For example, Base, which is the one that's bundled with GHC, which has all the common definitions that we saw, like maybe and bool and so on. And then I just do package, and normally that's enough. So in this case, the first hit is already the base library. And then for each such library, it looks like this. So it's the title and the modules that are in there. And sometimes there is like a README or some explanatory text, in this case not. And then all the available versions. And I mean, as you see, what other libraries it depends on. License, information about the author and the source repository and all these things. And then you can, for example, look into, let's see whether there's one, for example, data pool. So you can just look at it, and then, internet is slow, okay. So then you see information about what's in the module. So for example, here we see that indeed bool is just defined in the library, so it's not built into the language, it's just defined. Data bool with constructors false and true. We can ignore this for now. Then you see functions that are defined on booleans, for example, not. It's also possible to click on source, and then you see the corresponding source code defining it. What's also nice is you can do Control S, and for example, I don't know, vertical bar, and then you basically globally search in this package or in this module, so you can easily find something. And I wanted to do this now because I wanted to show you the dollar operator. So let's go back here. And sometimes it doesn't work.
Because you're outside the module.
Do I have to be in a module?
Yeah.
Do you happen to know a prelude, probably? I'm not sure I have to. Okay. So here's input called, yeah, try. Where was it? Here. Yeah. So you can ignore this. This looks complicated. But just the definition of the dollar operator. So f $x is just f applied to x. So it's basically just function application. So you might wonder why this is useful. So I mean, we can try it out. So let me just open the REPL. Make that bigger as well, I suppose. And hope make some of the right bar disappear. So I mean, let's say take any function. Let me, just to have more examples, import this data.character again. And we had, for example, this toUpper function to turn a lowercase letter into an uppercase letter. And now I can instead use the dollar operator and write this like that. And then, of course, you would ask yourself, why would I ever want to do this? But the cool thing is when you nest functions. So if you look at I for dollar, we see it has its right associative, and it has a very low precedence. And what that means, and normal function application is left associative. So if we take a function with lm, for example, this recall lm that checks whether an element is included in a list. So it's a function with two variables. So if I write lm q Kenya, for example, so then because normal function application is left associative, that's the same as this. So in this case, I don't need parentheses. But sometimes we want to apply a function and then another function. So for example, show toUpper q. So it will first turn the q into an uppercase q and then show it, so which will just be the string containing like single quotes and Q. So and in this case, I do need the parentheses, because if I leave them out, I will get an error. Because now I mean, if I leave them, as I just explained, because function application is left associative, it would mean this, and this doesn't make any sense, because to upper is a function, it's not showable, and even if it was, this result would be a string, and it makes no sense to apply a string to a character. So I need the parentheses, so the parentheses are needed. And we don't like parentheses as Haskellers. And using the dollar, I can write that much neater like this. So the dollar helps avoiding parentheses. And in this example, I mean, it's debatable. Even though, I mean, I always use the dollar even in this example, but especially if you nest deeper. So yesterday we had examples with, maybe I should, do I dare? I'm sorry? What was the first you said? Oh, yeah. I mean, for example, there's a function head that takes the first element of a list. So head of Kenya is the character K, which, by the way, is one of the functions that people don't like, because if you do the head of an empty list, you get an exception. And normally, so yeah, anyway, but we have this. So I could do head of Kenya, and then to lower, maybe, to lower, and then show it. So now I have like two nested parentheses, and using the dollar, I can just very neatly write it so. So that often makes it, I mean, yesterday we had examples with this tree, for example. I mean, there were like 3 nestings. Or when I did iterated transaction processing, and you want to take the result of the first rotation, apply something else, and apply something. I mean, you tend to have this, that you have lots of closing parentheses at the end. And with the dollar, it's much neater, and one can avoid that. So I'm using that all the time, and I had to really like be disciplined yesterday and day before yesterday not to use the dollar, but I am tired of that, so now I want to start using it. That's why I wanted to show you. But it's just function application, so it's really just for convenience, that it's easier to read and to write, and you don't need so many parentheses. It has a very trivial looking definition, as you saw. $x is just defined as f applied to x. Okay. With this out of the way, let's go back to the slides. Let's take this first of a pair, x, y is x. So what's the type of that? And there is not just one type we could give. We do this. Let's hide import prelude hiding first. So if I say first x, y is x, and now want to give a type annotation. So for example, 42 gives me Kenya. But I could also say this has type whatever. I mean, I could say the first is arbitrary and the second is Boolean. And then, of course, it's to A. So that would also compile. And I could try it for example, A is int. No, not int. A string. No, it's, yeah. Kenya, true. Gives me Kenya, or I mean, doesn't have to. I can also do bool, false, true. So yes. So there are all sorts of types. Another possible type would be A, A. Picks the first one. So the question is, which one should I pick? Because I just said that we have type inference in Haskell, so the compiler can always, you don't really need these signatures, so the compiler can always figure it out. But now we saw that there are many options. Let's just check on the slides. So here's just an example. Some of them I showed you, some I didn't. But so there are lots of different options. So is there one that's in some sense the best one? Does anybody have an opinion? Yes. And why? Exactly. So there's always in Haskell, at least if we ignore like fancy language extensions, there's always one type that is the most general one that covers all other possible types that you can give to an expression. In this case, it's that one. The others are specializations of that one. For example, the first one is the specialization where b equals a. The second one is the specialization where a equals int and b equals a, and so on. The third one is where a and b both equal int, and the third one is where a equals int and b equals character. So by instantiating a and b to certain choices, you can recover all the other possibilities. And this is the only one with this property. So this is the most general type you can give it. And that always exists. So the Haskell type system has been designed in a way that there is always a most general type, and the compiler can automatically infer it. And that's the one that's most flexible, so all the others are specializations of that. So by setting type variables, if there are any type variables, to other type variables or to some other types, you can get all the other possible types of an expression. And yeah, as I just said, so this one is the most general one for first, and for example, you can get all these others by instantiating a and b to the right values.
Other situations where you need to, by using a specific type of
Yes, I would say so. For example, when I want to give you examples with ints, I always give a type annotation for int. And the reason is if I write something like, for example, 3 plus 4, then I get this annoying warning. And the reason is that literals like 3 and 4 in Haskell are overloaded, so they are not of type int. If you ask for the type of 3, it's not int, it basically says for every numeric type A, 3 is of that type. So if I do an example with 3, the compiler doesn't know whether I want int or, so if you paid attention, yesterday I often did type on, I did then something like this to give a hint to the compiler that I'm talking about ints and not some other numeric type. And sometimes, so for example, in that case, it might make sense to use like int, because then I don't have to, it's maybe a stupid example, but then if I want to demonstrate it, I wouldn't need a type annotation. I could just write 42. That's one example. So if you don't want type annotations, then it might make sense to make it precise. There are other, I can't think of a good example now, but there are sometimes situations where it does make sense to restrict it.
Maybe for optimization reasons, you want the end user to use a specific implementation instead of all the possible ones. So you force the user of the function to use a specific type.
Yes, so there are some examples where it makes sense. Right. Then one thing, Haskell, the way the compiler works, so at runtime, all the type information is erased. And, right, you can only use it, according to the types. Yes? Okay.
In the chat?
Yes?
Nice.
Do we want to read?
Can you read?
Is it better the more general type of functions or the more restrictive?
We come to that in a moment. There was a question to that already. So sometimes there are situations where you want a more restrictive type, but I think normally most cases you want the most general one. Yes. But there are special cases where sometimes a more restricted makes sense. And so if we now use the most general type, which by the way is also the type that here this extension I'm using automatically suggests, and the extension is using the Haskell compiler under the hood. So just to demonstrate that the compiler always infers the most general type. So let's do this now. And now if I want a restricted version, I can, for example, restrict it first. What's the example on the slides? Int. So if I now want this, like another version, I can just write this. So it's always okay. So even though first is more general, I can use it in more restricted situations. So I can define the restricted version in terms of the general one. So I mean, I can try this out. I get this annoying warning because I'm not using the Y, so I can replace it with an underscore. So I can use this restricted first, 4237. But now this wouldn't work for 42 true because, I mean, it's now restricted to int. But I can't do the other way around. So if I now want to have a first prime, A, B to A, first prime is restricted first, then I will get a compiler error. And it says couldn't match A with int.